This video is on voltaic cells. So voltaic cells are when you have energy released in a spontaneous reaction that may be used to perform electrical work. So what you're doing is you're having a chemical reaction that is producing electricity. All right, so chemical energy is transferred into electrical energy. Make sure you understand spontaneous. Spontaneous means it will happen without help, so on its own. So there's nothing that you have to do to make this occur. Voltaic cells are devices in which electron transfer occurs via an external circuit. So the electrons are going through a wire, and it utilizes spontaneous reactions, so reactions that happen on their own. So this would be something like if we had, let's see, Zn as a solid, so solid zinc, and reacted it with copper 2 nitrate solution. Okay, so this reaction will happen on its own spontaneously because zinc is more active than copper. So you're going to get zinc nitrate solution and solid copper. And the nitrate in this case will be a spectator ion because it's not changing. It's part of the copper solution and then it's part of the zinc solution. So if we ignore that, this is the part we really care about right here, is how the zinc goes from a 0 oxidation state to a +2, and the copper goes from a +2 to a 0. So if we think about our half reactions here, we've got oxidation. So if zinc's going from 0 to +2, that means it has to lose electrons. So we've got here zinc solid that turns into zinc with a +2 charge, and 2 electrons will be lost here. So this is our oxidation, and this happens at the anode. When we talk about our voltaic cell, we have an anode and a cathode. The anode side is the negative side. Okay, so then the reduction is happening with the copper because you're going from a copper +2 in your aqueous solution. You have to add 2 electrons to that to turn it into a copper solid, which would have an oxidation state of 0. So this is your reduction, and this happens, we call this, where this happens, the cathode. Okay, and this would have a positive charge. So you're going to have to remember that oxidation happens at the anode, reduction happens at the cathode. So one way to do that is to think about oxidation is an O, anode is an A. These are both vowels. Reduction as with R, cathode with C. These are both consonants. That's one way to remember it. Another way is to think of an ox and red cat. So an ox for anode oxidation, red cat for reduction, cathode. All right, so here's what it looks like. Here's what a voltaic cell actually is. So you've got your 2 beakers with your metals and your solutions. I'm going to label some stuff here. So this metal here is my zinc. So there's my zinc solid. And the solution it's sitting in is my zinc nitrate. Okay. And then on the other side, this is my copper solid sitting in my copper nitrate. Oops. Okay. So we've got some connections now between our 2 beakers. The first is from the metal to the metal. This is a wire right here. And this is, I'm going to label external wire. This is where our electricity flows. So here's where our electrons are transferring, and they're going this way. Okay. This right here in the middle, it kind of got cut off right here. This is our voltmeter. So it measures how much voltage. In the middle here, this piece right here, this is what we call the salt bridge. And the salt bridge is, it could be tubing, it could be just some sort of even like fabric or tissue that allows salts or ionic compounds to travel through it. So in the salt bridge, In this case, our cations are going to go this way, and our anions are going to go this way. And the reason is because we have oxidation at the anode and reduction at the cathode, and let's label those. So if we go back up here, remember zinc is what's being oxidized. So if zinc's being oxidized, it's at the anode. So this beaker, this side, is my anode. Oops. Okay, so here's my negative charge, and this is where my oxidation is happening, which makes this my cathode, right? And here's my positive, and here's where my reduction is happening. Okay, so I'll show you in class kind of a simulation, but what's really happening here is we have our zinc solid right here, and the electrons are leaving it, right? They're going up and through the wire. And when the electrons leave the zinc, we're left with cations of zinc, which then go into this solution, which will react with the anions that are coming over of the nitrate. So you're making more zinc nitrate. Some of those cations, are going back the other way over here and reacting with some of the nitrate over here. So the electrons, right, as they leave the zinc, they go up through the wire and they go into the copper. So as they go, right, because copper gained electrons right here, so they're going to go through the wire, and some of these cations are going to be these copper cations, Cu plus 2. When you add the electrons to it, they turn into solid copper. So then you're making more solid copper. All right, so a little bit more. So a salt bridge is a porous barrier. It's used to complete the circuit, right? You got to have it all the way complete for electricity to flow. Cations always move from anode to cathode, so from negative to positive. Anions move from cathode, so positive to negative to anode. Solid metals are the electrodes, so we call those the solid zinc and copper in this case. We call them electrodes. Cathode and anode are your electrodes. Electrons flow from anode to cathode. Right, your negative to cathode. So the anode is always negative then, and your cathode is always positive in a voltaic cell. Electrons can't flow through solution, so they have to be transported through your external wire. Right, they're going up and around. They can't go in your solution. Anions and cations move through the salt bridge. And let's see, cations move into the cathodic compartment to neutralize the excess negatively charged ions. Right, that makes sense, right? Cations are going to neutralize your negative. They're going to bond with your negatively charged ions. Anions move through the anodic compartment to neutralize the excess positive ions. Okay, so one last piece of this, a way to diagram this. So we know, like, I don't have to draw this every time to realize, oops, sorry about that. I don't have to draw this to realize what's happening in my voltaic cell. We can draw what's called cell notation, cell diagram notation. So cell diagram notation, kind of here's your general format, is going to be your anode, solid, okay, and then a line, and then it's going to be your cation at anode, and then a double line. I'll explain what the lines mean in a second. And then it's going to be your cation at cathode, and then your cathode solid. All right, these lines here and here, these are indicating the phase boundaries. And the double line in the middle is representing your salt bridge. Let's see, electrons are flowing this way. right? So we're always doing anode to cathode. So anode's always over here, cathode's always over here. All right, so let's draw our cell diagram notation for this particular voltaic cell. So we have, let's see, at our anode, our solid was zinc. So we've got zinc solid, and then we have zinc plus 2 is what's in our aqueous solution. Okay, then we have our salt bridge. Then our cation in our cathode is that copper plus 2 aqueous. And then our electrode on the cathode side is our copper solid. So this is your cell diagram notation for this particular voltaic cell. So like I said, we'll go through some simulations to see kind of more of what's happening. Make sure you look over the terms. It's really important we understand what's happening at the anode, the cathode, the charge, what's flowing where, and everything in this type of cell.